Picture yourself standing on the barren, cratered surface of the moon. Above you, the blackness of space stretches endlessly, interrupted only by the stark white glow of the distant Earth. Suddenly, a futuristic device begins to unfold, a shimmering accordion-like array of solar panels, delicately engineered but robust enough to withstand cosmic radiation and lunar dust storms. This breathtaking scene is not just a fantasy for science fiction novels or an artist's concept in a NASA press release. It is a vision now backed by billions of dollars, international rivalry, and the relentless march of technology. Humanity stands at the edge of a new era, one where space itself could become the next great frontier in the battle for clean, abundant energy. But as with any grand ambition, the path is riddled with obstacles both technical and geopolitical. The central question remains: will space-based solar power, known in the industry as SBSP, finally light up our world, or will it remain an unfulfilled promise, forever on the technological horizon? But when the fever of the oil crisis broke and the world's attention shifted, the dream of space-based solar power seemed to fade into the background. Early engineering studies revealed daunting hurdles. Launching vast arrays into orbit, each as large as a football field or even a small city, proved astronomically expensive. The cost of placing just 1 kilogram into low Earth orbit hovered around tens of thousands of dollars in those days, making commercial viability a distant hope. Even more challenging was the question of transmission. How do you safely and efficiently send gigawatts of energy across thousands of kilometers through a turbulent atmosphere without losing most of it along the way? The technical answers centered around microwave or laser transmission, but these methods introduced their own problems. Atmospheric disturbances, energy loss over long distances, and concerns about environmental or health impacts all contributed to skepticism. As global oil prices stabilized and government research funding dried up, the idea of SBSP was quietly shelved by many. For decades, it remained the province of a few dedicated scientists, science fiction writers, and the occasional think tank white paper. Fast forward to the 21st century, and a new set of forces is breathing life into this grand vision. The world is once again searching for energy solutions, this time to combat climate change and meet the explosive growth in demand from developing regions and emerging technologies like artificial intelligence. At the same time, a revolution has swept through materials science and aerospace engineering. New lightweight, radiation-resistant composites have slashed the mass and cost of space structures. Private companies, emboldened by government contracts and venture capital, are pushing the boundaries of what is possible. Enter Atomic 6, a dynamic startup based in Marietta, Georgia, just outside Atlanta. Founded by Trevor Smith, Atomic 6 specializes in building advanced carbon fiber structures designed for the extreme environments of space. Their flagship innovation, the Lightwing, is not just another solar panel, it is an engineering marvel. Unlike the rigid, glassy panels you might see atop a suburban rooftop, Lightwing is made up of flexible, accordion-like carbon fiber panels attached to a strong but featherweight tube. When launched, the array is tightly compressed, but once in orbit or on the lunar surface, it unfurls gracefully, maximizing surface area and minimizing weight. The numbers behind Lightwing are astonishing. Its power-to-mass ratio exceeds 200 watts per kilogram, making it at least 4 times more efficient than conventional solar arrays used in space today. To put this in perspective, traditional arrays require heavy structural supports and thick glass covers to survive the rigors of space, but Lightwing's clever design leverages cutting-edge composites that are both lighter and more resilient to radiation and micrometeoroids. Furthermore, Atomic 6's proprietary space mass technology boosts structural stiffness by 15% compared to standard composites, a critical edge when dealing with the unpredictable forces of launch and the violent vibrations of landing on the moon. Atomic 6's innovation has not gone unnoticed. The company has already secured more than $12 million in research contracts from the United States Department of Defense. Its latest coup, a $2 million contract from the United States Space Force, focused on subjecting Lightwing to the most brutal flight qualification tests imaginable. These simulations replicate the searing heat and bone-chilling cold of space, the deafening roar of rocket launches, and the airless, radiation-soaked vacuum beyond Earth's atmosphere. The goal is simple but daunting: to prove that Lightwing can survive and operate flawlessly in the most hostile environments known to humankind. The company's ambitions go far beyond just powering satellites. One of Atomic 6's clients plans to mount the Lightwing on a satellite data center scheduled for launch in the early months of 2027. Even more audacious is the plan to plant a 150-foot-tall light-wing array at the Moon's south pole, a region of constant sunlight, ideal for both mining operations and human habitats. For the first time, there is a plausible route to providing round-the-clock power on the lunar surface, a game-changer for everything from scientific research to resource extraction and even permanent settlement. The economic stakes could not be higher. The global market for space-based solar power was valued at roughly $635 million in 2024, but according to industry analysts, it is projected to more than double by the end of this decade, topping $1,440 million by 2030. That growth is driven not just by technological progress, but by a mounting recognition among governments that space is quickly becoming a strategic asset, an arena where energy, security, and geopolitical influence intersect. Consider the raw numbers. A space-based solar panel can generate up to 2,000 gigawatts of continuous power, 40 times more than a similarly sized panel on Earth, which must contend with nightfall, weather, and atmospheric absorption. This advantage opens up a world of possibilities. Imagine entire cities powered by energy beamed down from orbit, or remote military outposts and research stations sustained indefinitely by orbital power plants. For lunar mining colonies, where the sun may shine continuously for weeks at a time, robust solar arrays like Lightwing could enable round-the-clock operations, fueling the extraction of rare Earth elements, water ice, and other resources vital for deep space exploration. Yet for all this promise, there are profound doubts and complex challenges. In 2024, NASA's Office of Technology, Policy, and Strategy published a sobering report. The agency estimated that the cost of delivering just 1 megawatt of space-based solar power could range from $900,000 to $1,300,000, a figure that dwarfs the cost of most terrestrial power sources. Some critics argue that these costs could render SBSP uncompetitive for the foreseeable future, especially when compared to rapidly falling prices for Earth-based renewables like wind and solar. However, not everyone agrees with this pessimistic assessment. Martin Soltau, a respected industry analyst, has publicly challenged NASA's findings, arguing that the report is wide of the mark and fails to account for rapidly declining launch costs and the accelerating pace of technological innovation. Similarly, Tim Peake, the renowned astronaut with the European Space Agency, points out that space-based solar farms will only be viable once launch costs come down. The argument here is straightforward. As space transportation becomes more routine and affordable, the economics of SBSP could shift dramatically in its favor. Indeed, the last decade has seen a revolution in launch technology. Companies like SpaceX, Blue Origin, and Rocket Lab have driven down the price of reaching orbit, while advances in reusability promise even greater savings. In the 1970s, launching a kilogram into low Earth orbit cost the equivalent of tens of thousands of dollars. Today, it is possible for a fraction of that, a trend that could accelerate as new heavy-lift rockets and spaceports come online around the world. But cost is only one piece of the puzzle. Space is not just a domain for engineers and entrepreneurs. It is rapidly becoming a new theater of geopolitical rivalry. The militarization of space and the rise of state-backed competitors like China add layers of complexity and risk. China's ambitions are monumental. Their government has publicly compared its own space solar program to building another Three Gorges Dam. Only this time, the infrastructure floats silently above our heads. The potential for sabotage, espionage, or outright conflict over these critical assets is real and growing. Security experts warn that space-based solar arrays and the ground stations that receive their energy are vulnerable to both physical and cyber attacks. What if a hostile nation jams the energy beam or disables a satellite with an anti-satellite weapon? What if hackers infiltrate the control systems, shutting down power or redirecting it to unintended locations? As the world races to deploy SBSP infrastructure, international rules and safeguards for wireless energy transmission are still being debated. The lack of clear protocols raises the specter of accidental interference, deliberate sabotage, or even catastrophic accidents. Beyond the immediate risks, the rise of SBSP could fundamentally alter the balance of power on Earth. Nations that control orbital energy infrastructure may gain outsized influence over global energy markets, supply chains, and even the resilience of national power grids. In a future where cities, industries, and military bases depend on energy beamed from space, the stakes for security and sovereignty become existential. Some analysts have even suggested that the next great domain of conflict may play out not in the skies or cyberspace, but in the invisible infrastructure that delivers power to billions. Yet for all the danger, the opportunity is immense. If Atomic 6's light-wing technology survives its qualification tests and proves reliable in orbit, it could trigger a cascade of innovation. The company's power-to-mass breakthrough means that more ambitious space stations, high-capacity data centers, and even permanent lunar outposts could be powered by arrays that are lighter, easier to launch, and more efficient than anything previously possible. Unlike the space mirrors or massive orbital behemoths envisioned in the last century, these new arrays are modular, scalable, and designed for rapid deployment. These are not just theoretical possibilities. Atomic 6's technology is already being integrated by clients like Starpath Robotics, who are developing deployable booms for lunar solar applications. The company's expertise in composites has even spilled over into terrestrial industries, with products like the Carbon Corvette Vive 2.0 wingless aero package, improving the aerodynamics of high-performance vehicles. This cross-pollination of innovation demonstrates how breakthroughs in space can ripple through the broader economy, creating jobs, new industries, and unforeseen opportunities. According to Adlan, an executive at Space Solar, pursuing space-based solar power is a no-regrets move, creating jobs and empowering supporting technologies. He underscores the fact that even if SBSP itself takes years to reach commercial maturity, the technologies developed along the way will have far-reaching benefits: lighter materials, better batteries, more resilient electronics, and advanced anti-collision systems for crowded orbits. NASA itself, despite its cautious economic outlook, acknowledges the environmental imperative. The agency's Office of Technology, Policy, and Strategy notes that SBSP can reduce reliance on fossil fuels and lower greenhouse gas emissions, a critical benefit as the world struggles to decarbonize its energy supply. Unlike terrestrial renewables, which are subject to local weather and the day-night cycle, space-based solar can deliver continuous baseload power, transforming the economics of clean energy, especially in regions with limited sunlight or unstable grids. The global push for SBSP is now well underway. The United States Space Force has invested more than $237 million in its STEP 2.0 program, aimed at developing next-generation satellite technologies. China, the European Union, Japan, and even private consortia are all racing to prove out their own concepts. The next few years will see an unprecedented number of test deployments, technology demonstrations, and, inevitably, setbacks. For Atomic 6, the immediate challenge is to validate Lightwing's performance under real-world conditions. The qualification tests, which take between 12 and 18 months, are designed to simulate the stresses of launch, the radiation of deep space, and the complex mechanical loads encountered during deployment. Success here would open the door to major contracts, not just for lunar or orbital arrays, but for missions to Mars, asteroid mining expeditions, and the emerging private space station market. But the story does not end there. The ultimate success of SBSP will require more than just clever engineering. International cooperation, robust security protocols, and clear standards for wireless energy transmission must all be developed. As with the development of the Internet or global air traffic control, the creation of a reliable, secure, and universally accessible orbital power grid will demand negotiation, diplomacy, and the alignment of national interests. So, what does all this mean for you, the viewer, the citizen, the future customer of orbital energy? The lesson is both simple and profound. The age of space-based energy is no longer a distant dream. It is being built right now, in labs and on launch pads you may never have heard of, by engineers whose names are only beginning to appear in the headlines. In less than a decade, the price you pay for electricity, or the resilience of your country's power grid, could be shaped by decisions made in orbit today. For those following this story, it is clear: the convergence of materials science, aerospace engineering, cybersecurity, and energy policy is ushering in the next industrial revolution. SBSP is not just about cheap power or lunar mining. It is a catalyst for advances in everything from lightweight composites to autonomous robotics, from global communications to distributed computing. As astronaut Chris Hadfield, now an advisor to Atomic 6, puts it, "The things we're building aren't just for space. They're building a new future for everyone." Looking ahead, the scenarios are both exhilarating and daunting. Imagine a world where every city, every village, every remote research station has access to clean, uninterrupted power, where lunar bases hum with activity, and Mars outposts rely on solar arrays made from lunar regolith. But also imagine a world where the weaponization of space and the fragility of orbital infrastructure introduce new vulnerabilities, where energy becomes a tool of diplomacy or even coercion in the hands of a few powerful actors. The next decade will be decisive. If costs continue to fall, and if companies like Atomic 6 can prove the reliability and scalability of their solutions, we may soon witness the dawn of a truly global, space-powered civilization. But success is not guaranteed. Technical hurdles remain, from safe wireless power transmission to the development of in-situ manufacturing on the Moon and Mars. And the specter of geopolitical rivalry will not disappear overnight. If you are excited by these possibilities, if you want to understand how space technology is shaping not just tomorrow's rockets but tomorrow's economy, make sure you subscribe and hit the bell for regular updates. Drop your thoughts in the comments. Will space-based solar power succeed, or are the risks simply too great? Do you